everybody, it's Miss Maneely, and I am going to quickly go through the Chapter 3 review with you on modeling linear relationships. In problem number 1, you're given 6 different scatter plots and 6 different correlation coefficients. I think the easiest thing to do is to sort of look for the relationships that are negative and look for the relationships that are positive and kind of zero it in that way. And I can see from my answer choices that I have only one positive correlation coefficient. So that should be the easiest association for me to distinguish from the others. And I think the one that looks the most positive would be letter C. And sometimes it helps to sort of draw a circle or an oval around your points. So C is going to correspond, I think, to the only positive association. So I'm going to cross that off my list. The other one that I think will be easy to identify is the one that has a 0 as its correlation. And I think that's going to closely resemble the graph of letter D. So when I look at it, I can't really tell the direction that it's going. So that would be a correlation of 0. And then the rest are all negative associations. So I'm going to start with the one that is the strongest. And I know that's going to have a correlation of negative 0.9. The one that's most linear is going to correspond to letter A. And then I'm just going to kind of go in the decreasing strength. And it looks like B would be the next strongest. And I'm going to call that R equals negative 0.75. And then the next strongest would be, it looks like E, which I would say is negative 0.5. And then the one that is the least strong would be R equals negative 0.1. Okay. In number 2, you're given some data. It says an insurance company conducts a survey of 15 of its life insurance agents. The average number of minutes spent with each potential customer and the number of policies sold in a week are noted for each agent in the table below. So we're given some information about the average number of minutes, the number of policies sold. Before we start entering the data, we should probably pay attention to which variable represents our explanatory and which is the response. Since I'm going to expect that the more time I spend with customers, the more policies I'd expect to sell, my explanatory variable then is going to be the average number of minutes. And remember, your explanatory variable is going to be your x variable. My y variable then would be my dependent or my response variable, and that's going to be the number of policies sold. And I do expect there to be a positive association here. So I've already got the data in my calculator in lists 1 and 2. And I'm going to go ahead and construct a scatter plot. So if I go into y equals, I'm going to make sure that I pull my x's from list 1 because that's where I store them. And my y's I'm going to pull from list 2. Let me make sure I don't have an equation. Oops. In y equals, it looks like I do, so I'm going to clear that out. And then I'll go ahead and zoom 9. And so there's my scatter plot. I'm going to go ahead and do a screenshot of this. Okay, and all I ask you to do is to just provide me a sketch on your paper and then make sure you label your axes. Okay, so we know that the x variable is my average number of minutes and my y is going to be the number of policies. And you're asked to describe the association. And remember, when you're describing the association, it's just going to be a very general description of the strength, the direction, and the form. And remember, you always want to use the context of the problem. So I can say that there's a strong positive association . And then I also want to kind of link in the context here. So the more time spent with a customer, more policies are sold. I also want to mention the form here. I think it's obvious that a nonlinear that a nonlinear model would not be appropriate, that this is a linear association. Okay. It says to determine the equation for the least squares regression line. Your calculator can do this. Go to your home screen, Stat, calc, and then there's two different options for doing linear regression. I'm just going to use option 4. You want to make sure you let the calculator know where you're pulling the data. So I'm pulling my x's from list 1 and my y's from list 2. You can ignore the frequency list, but the next piece is very important. You want to store the regression equation in y1. So go to vars, yvars, function, and then choose the y variable you want to use. I'm just going to go ahead and use y1. And then when you go to calculate, you'll start to see, well, it went away too fast. If you have one of the older calculators, you're just going to use linear regression and then choose list 1, comma, list 2, comma, and then do your vars, yvars function and choose y1. So you're just going to be listing the command as a string. Notice on the calculator the form of the equation. It's in the equation ax plus b. The other regression command is going to be a plus bx. So just pay attention to which number is your slope and which is your y-intercept. It doesn't matter which command you use. Make sure you put a hat on your y when you write the equation. And so in this case, my a variable is my slope, so that's going to be 0.549 x minus 1.731. Notice also that my calculator reports both my r and my r squared value. If yours doesn't, then you need to go to your catalog, which is second 0, and then scroll down to the d's, or simply just press D, and that'll take you down to all of your D commands. And you want to find the command that says diagnostics on, and then press enter until it says done. And then if you go back and try your linear regression again, you should see the r and the r squared value. In part D, we're asked to interpret the slope and the y-intercept. So remember, with your slope, we always reduce it to as x increases by 1 unit, except we want to make sure that we're using the context of the problem. So in this case, my x value represents the number of minutes spent with a customer. So I want to say as the number of minutes per customer, or it should be maybe the average number of minutes per customer, increases by 1 minute. We would expect, or we predict, that my y value is either going to increase or decrease by my slope. And in this case, because my slope is positive, we predict that instead of saying y, I'll use the average number, or I'm sorry, the number of policies sold, that the number of policies increases by what was our slope? 0.549? Okay, and make sure you include that. It's a prediction or an expectation. If you don't state that, then it kind of makes it seem as though we expect this for every single, that it's a constant rate of change, that it's perfectly linear, and that relationship exists across the board, and that's not necessarily true. Our y-intercept basically gives us the value of y when x is 0. And so the value of y would be the number of policies sold. So let's see. So when the time spent with customers is 0, we'd expect the number of policies sold to be negative 1.731. And this illustrates something that we talked about earlier about extrapolation. Extrapolation occurs when you're trying to make a prediction that goes too far beyond the data that you've collected. And oftentimes you're going to find that with the y-intercept. Like our data, I think the lowest data value in terms of our minutes, the lowest number is 18, and it looks like the largest is 33. So my domain goes from 18 to 33 minutes. If I try to make a prediction that's too far beyond that, then I can't really rely on my model anymore because I don't have any data to support it. And so that's why sometimes your y-intercept is going to look like nonsense. Obviously, you can't sell negative number of policies. In letter E, it says, what's the correlation coefficient, and what does this value tell you about your linear model? So the correlation coefficient, again, the calculator reports it as r equals 0.88. I'll go ahead and round that to 4. Always give me 3 decimal places. And this confirms, so this value confirms that we remember how we said that we thought it was a strong positive association. So this value confirms that there is a strong positive association between the variables. When we couple that with the scatter plot, I think it's obvious that we can conclude that a linear model is appropriate. But let's go ahead and use the residual plot. So to construct a residual plot, we need to first of all find the residuals. We do that by going into our lists. So we have our actual x's in list 1, our actual y's in list 2, and we want to put our predicted y's in list 3. And I do that by going to the tip top of my list, and I want to basically evaluate my function, y1, for all the values that are in list 1. And I'm going to use function notation to do that. So I'm going to go to vars, y vars, function, and choose my equation, which is y1. And then I'm going to use the parentheses not to represent multiplication, but to actually represent function notation. And I'm going to enter in, I want all the values in list 1. And so this command will essentially plug every single x value into my equation and evaluate it. And what I hope to see is that list 2 and list 3 are the same. Obviously, they're a little bit different. And to determine how different they are, I find my residuals. And so the residuals are always going to be your actual y values minus the predicted. And so in my lists, that would be list 2 minus list 3. And so what I'd like to see in list 4 is that all those values are 0. And actually one of them is 0, but they're all relatively small. To construct the residual plot, I'm going to go back into my scatter plot options, and back into my plot options. I'm going to choose the same scatter plot I had before. My x's stay the same, because so I'm still plotting over my x values. But instead of pulling up my y's, I want to pull up my residuals, which I stored in list 4. And now I can zoom 9, and that'll give me my residual plot. And so what we hope to see in our residual plot is a random scatter of points above and below the line. Because remember, that line right there is my regression equation. And in this case, it is a line. So it's my regression line. And so since there's a random scatter of points, and it's evenly spread above and below, we can conclude that our model is appropriate. And our calculator did find the line of best fit. So our linear equation is going to be the best linear equation there is. In letter G, it says for an agent who spends an average of 46 minutes with each potential customer, how many policies would he or she expect to sell? So we can do this on our home screen, and I'm going to use the similar command that I used in my lists. I want to evaluate my equation when x is 46. But if I type in my regression equation by hand, like if I enter these numbers into my calculator, I'm rounding. And I don't want to do that because then my answer is going to be a little bit off. But remember, we stored our regression equation in y1. So I'm going to pull it up on my home screen. And I'm going to use function notation. So in parentheses, I'm going to evaluate my equation at 46. And my prediction is 23.534 policies. Okay. And then the next question is, how confident are you in the prediction, and explain? Well, even though we have a good model, which is great, because if I have a good model, then it makes sense to make predictions. The other question I have to ask myself is it appropriate to make a prediction for 46 minutes? And this is where I need to go back into my data and take another look at my domain. And remember, my data collected goes from 18 minutes per customer to 33 minutes per customer. So if I wanted to make a prediction at like maybe 35 or 38 minutes, that would probably be okay. But 46 minutes away, that's far beyond my data set. And so this is what we call extrapolation. So since 46, is far beyond the data that is collected, or the domain of the data collected. I'm not confident in my prediction. We have no data to support our model or to support a linear model. Oops. Beyond, what was it, 33 minutes? Okay, so I don't really know that a linear relationship is going to continue. So I don't want to use my equation to make predictions too far away. All right, so let's take a look at the next one. In number 3, it says a random sample of 30 U.S. farm regions surveyed during the summer of 2008 produced the following statistics. It says the average temperature during the growing season was 81 degrees with a standard deviation of 3. And I think I've changed this problem on your paper, so it might look a little bit different. So I'm going to answer the questions that you guys have in front of you. I think I changed the format a little bit. We also have the average corn yield, and this is in bushels. Okay. And so we also are given the correlation coefficient, which tells us that R is equal to 0.32. It asks us to state the explanatory and the response variable. Well, this is one that you have to think about. Would I expect the temperature to explain the corn yield, or would I expect the corn yield to explain the temperature? And so I think it's probably pretty obvious that our explanatory variable is going to be the average temperature, and the response is going to be our average yield. Okay, and just remember that it's very important that you distinguish between your explanatory and response variables correctly, because you need to figure out which variable is x and which variable is y. When you're determining your slope and y-intercept from the summary statistics, it's important that you're using the correct order of the terms. So in part B, it says to determine the slope. So remember, from Algebra 1, slope is rise over run. When we're calculating it from like a table of values, we know it's the change of y over the change in x. Well, now we're not looking just at how the x's and y's are changing. We're looking at the deviations. So I'm going to look at the standard deviation of y. And actually, let me go ahead and put my x and y here so it makes it a little bit more easy to see. And I believe that like I said, I think I changed this on your paper. Okay, so our slope, we're going to take our standard deviation, and just like I said before, the change in y over the change in x, and that's going to correspond to the standard deviation in y, which is going to be 5, over the standard deviation in x, which is 3. But then I have to remember that my slope could be positive or negative, and standard deviation is always positive. So in order to get the direction of my line, I need to take into consideration my correlation coefficient. So I also need to multiply by that. And so the slope of my line, if I take 0.32 times 5/3, we get 0.5333. Okay, and then let's think about what the units would be for that. Because my y variable goes on top, I want to make sure I use my y units, which would be bushels. And then on the bottom would be my, my x variable, which would be in degrees Fahrenheit. And to interpret that, I would basically say, and remember we always reduce it to as x increases by 1 unit, so as the average temperature increases by 1 degree, and I'm going to go ahead and throw in my Fahrenheit. And remember, it's just an expectation or a prediction. We predict the average corn yield to, in this case, since my slope is positive, we expect it to increase by 0.533 bushels. The y-intercept, remember you can determine the y-intercept if you know a point on the line and the slope. And the point on every line of best fit is going to be x bar, y bar. And we know the mean of x and the mean of y. And so if we take our mean of y, which is 131, and subtract my slope, times the mean of x, which I know is 81, that will give me my y-intercept. So I'm going to do 131 minus, I'm not going to want a rounding error, so I'm going to hit second answer, and that'll call up my previous command, times 81, and that'll give me 87.8. That's a y value, so that corresponds to bushels. So if I'm asked to interpret it, it basically means when the average temp is 0 degrees Fahrenheit, we expect a yield of 87.8 bushels of corn. And again, I don't know how realistic that is. If the average temperature is below freezing, I can't imagine that we would yield anything. So this is another example, even though your y-intercept isn't negative, it's another example of a y-intercept that may not make sense for this situation. Now let's put all those values together. Remember, with your line of best fit, you always want to put a hat on your y. Your slope is 0.533. That's going to go next to x plus your y-intercept. And then we're asked, based on the study, what is the mean predicted corn yield for a region where the average growing season temperature is 76.5? How confident are you in this prediction? So in this case, I don't have my equation stored in y equals, but again, I'm just letting x equal 76.5. So I'm just gonna type in a bunch of 3s so I don't have my error. Then I'm going to put in my x, 76.5, and then add my y-intercept to that, which is 87.8. And the prediction is 128. Looks like 128.6. And that would be, again, in bushels. And it says how confident are you in this prediction? Well, this is a little less obvious because I can't see the scatter plot. So I really can't tell if my linear model is appropriate because I don't see the points. But there's another measure that I am given, and that's my correlation coefficient. And I think you can see from the correlation coefficient that the association between these two variables is very weak. Another way that you can look at this is to square that. So if you actually square it, so since r squared is equal to, and if we do 0.32 squared, that gives us 0.1024. That tells us that only 10.24% of the variation in my y values, which in this case would be the corn yield, can be predicted by or explained by the regression line. On average temperature. So that's a very, very low amount. Only 10% of the time is my equation going to predict it correctly. So for that reason, I would probably conclude that that the prediction that I have is not very accurate. So I have to read the sentence again. So 10.24% of the variation in corn yield can be explained by the regression line on the average temperature. I am not confident in the prediction. You could also simply say, since the correlation coefficient is so close to 0, there is not, we would probably just go ahead and assume there is not a strong linear association, or just there's not a strong association between the variables, and therefore we wouldn't want to use a linear model to make the prediction. And you could say that also, and that would also give strength to your argument. All right, the last question, number 4, and this is how I would expect it to be presented on your AP exam, where you have a situation, you have a scatter plot, you have a residual plot, and then you have some summary statistics. So it says in number 4, many people believe that students learn better if they sit closer to the front of the classroom. Well, does sitting closer cause higher achievement, or do better students simply choose to sit in the front? To investigate, an AP statistics teacher randomly assigned students to seat locations in his classroom for a particular chapter. At the end of the chapter, he recorded the row number, row 1 is going to be closest to the front, and the test score for each student. Least squares regression was performed on the data, and a scatter plot with a regression line added, a residual plot, and some computer output from the regression are shown below. So I think you can see from the scatter plot, there's not a very strong association between these two variables at all. And from there, you may just conclude that it's not even worth constructing a linear model, because if there's not an association, why would you go any further? But it's been done for us, so let's continue with the problem. So letter A says, what is the equation of the least squares regression line that describes the relationship between row number and test score? Define any variables that you use. Well, there's a couple ways that you could go about determining the variables. If you read the problem, we know that we're dealing with row number and test score. Another way that we can determine our variables is to look at our graph. We have row number and test score. And then thirdly, if we look at the printout, we can see just the row number, and this is always going to be our explanatory variable. Okay, I also know that my row is going to be explanatory because it's on the x-axis, and my score is going to be on the y-axis. So let me just write this down. So if x represents the row number, y represents the test score, the next thing I need to do is determine the equation of the line. And this is actually given to me in this printout, and it's just a combination of those two numbers. Both of those numbers are listed under the word coefficient, and if you look at the words next to them, it kind of helps identify which is which. So the number that's next to the word constant is going to be your y-intercept, and the number that is listed next to your explanatory variable, which again, remember that's just x, is going to be your slope. So when you write your equation, just make sure you put a hat on your y, and that's going to be negative 1.1171x plus 85.706. In letter B, it says to calculate and interpret the correlation coefficient. Well, if you look at the printout, the value of r is not given, but you do have the value of r squared. Since r squared is equal to 4.7%, you want to remember that, change that back to a decimal. So the value of r is simply going to be the square root of 0.047. So if we do that, the square root of 0.047 is going to give you 0.217. Now, when you take the square root of r squared, you're always going to come up with a positive number. So it's up to you to determine whether or not the correlation coefficient is positive or negative. And there are a couple things you can look at to figure it out. I mean, if you look at the original graph, I think it's pretty obvious that the line is decreasing. So that should give you a clue that there's a negative association, so your r value should be negative. Another way that you can look is to look at your slope. If your slope is negative, then your correlation coefficient has to be negative. And if we interpret the correlation, basically that tells us there is, and I think because this value is so close to 0, I think we can go ahead and say there is a weak negative association between the variables. And we can go ahead and say, let's just go ahead and say between row number and test scores. However, I would not call this association linear. And if you're just interpreting the correlation coefficient, you don't necessarily have to add that last statement. That's more from the scatter plot. The correlation coefficient, remember, is just weak, or the strength and the direction. Now it says to interpret the coefficient of determination. So that goes back to our r squared value. So r squared, and you can leave it as 4.7% if you want. And remember, r squared is basically giving us the percentage of the variation in our y variable that can be explained by the regression equation on x. So we're basically saying only 4.7% of the variation, in this case the y represents our test scores, can be explained by or predicted by the regression equation on row number. Okay. And so if you couldn't tell from the correlation coefficient, the coefficient of determination, and the scatter plot itself that this is not a good model for our data, in fact, there's not really an association between the variables, so I don't know that you would be able to come up with a model for the data. The last statement is just adding again, is it appropriate to model these data using a linear equation? And this time, though, we're going to look at the residual plot and the standard deviation of the residuals. Now, here's the thing, when I look at the residual plot, and if I'm just glancing at it, I actually see a random scatter of points above and below the line, which is actually what I want to see. The other thing I want to consider, though, is how far the points are from the line. And we know just for thinking of it that since the residual represents a deviation, I'd like those deviations to be very small. So this is a time when you really want to take a look at the scale on your residual plot. Notice how far away those values are. And remember, we're talking about a prediction for test scores. So our predictions are 20 above and 20 below the actual score on a test. And if it's a 100-point test, which it looks like it is, we're talking about 2-letter grades. So even though there's a random scatter of points, you know, our line does kind of cut through those data points, they're all really scattered pretty far away from the graph. And again, looking at the residual plot alone is very subjective. So I want to quantify it in some way. And that's when I go back to using the standard deviation of my residuals, which is 10.067. So despite the fact that there's a random scatter around the plot, let's say this here. There is a random scatter of points above and below the regression line. However, the actual residuals are 20 above and 20 below. It can deviate fairly far from my regression equation. Let's see. We can just say the residuals are quite large, varying from 20 points below to 20 points above the actual scores. Okay, so in that case, I can kind of see that the model is not appropriate. The other thing I would want to look at is the standard deviation of the residuals. And so the standard deviation of the residuals and this is your S. S equals, what was it, 10.067. Tells us that our predictions the line's predictions will be over 10 points off on average. Okay, and so again, is the model appropriate? And the answer would be no. So just make sure you answer each question and provide enough justification that's not just subjective. So now we have a way to quantify everything. We have a way to quantify the association between two variables by looking at the correlation coefficient. Now you can also quantify your impression of a residual plot by looking at the standard deviation of the residuals. And again, I'm not going to ask you to calculate the standard deviation of the residuals. I will give you a problem like this and ask you to interpret it. So as long as you understand the interpretations, you should be fine on this test. Obviously, you have to be able to perform linear regression, you have to be able to construct a residual plot, calculate residuals, but the most important thing here is that you are able to interpret everything in the context of the problem. That not only are you able to come up with the linear equation, but you're able to determine whether or not it's appropriate to model the data with a linear equation and make predictions and determine how confident you are in the predictions that you get. So I hope this was helpful. Obviously, if there are things that you have questions on, please come in and see me on Monday during Bulldog Block, and I'm here to help. You can certainly email me over the weekend as well if you have questions, and I'll do my best. Good luck. Have a great weekend, guys.